You've probably heard the phrase, work smarter, not harder. And while there's wisdom in efficiency, what if I told you that the sheer act of hard studying, pushing your cognitive limits, is one of the most powerful ways to physically and functionally change your brain? Not just metaphorically. We're not talking about quick hacks or simple memorization tricks today. We're diving deep into the neuroscience and cognitive science behind intense effort. What really happens inside your skull when you're grinding through complex computer science problems, trying to debug code that seems impossible, or when you're a psychology student dissecting intricate theories of human behavior, wrestling with concepts that challenge your understanding. The answer is far more incredible than just learning. Your brain is actively remodeling itself. Let's start with the bedrock principle, neuroplasticity. This isn't some new age concept, it's hard science. Your brain isn't a fixed entity you're born with. It's dynamic, adaptable, constantly rewiring itself based on your experiences, actions, and efforts. Think of it like a muscle. The more you challenge it in specific ways, the stronger and more efficient it becomes in those areas. When you study hard, particularly complex, demanding subjects, you're triggering this process on a massive scale. So what does this look like in practice? Research provides concrete evidence. Studies using brain imaging techniques like fMRI have shown tangible changes. For example, research on individuals learning complex new skills, like juggling or mastering a new language, has demonstrated increases in gray matter density in specific brain regions associated with those skills. Gray matter contains neuron cell bodies. More density often correlates with enhanced processing power. When CS students grapple with algorithms and logical structures, areas like the prefrontal cortex, crucial for planning, complex problem solving, and decision making, get a serious workout. This consistent activation strengthens neural pathways, making those processes more efficient over time. Similarly, the hippocampus, vital for forming new memories, becomes highly active as you encode and retrieve complex information, whether it's data structures for a CS student or case studies for a psychology student. Intense study strengthens these memory circuits. Furthermore, it's not just about strengthening existing connections, it's about synaptic plasticity. Every time you learn something new or reinforce existing knowledge through focused effort, the synapses, the tiny junctions between your neurons, change. They can become stronger, making communication between specific neurons faster and more reliable. You're essentially building more robust and efficient information highways in your brain, specifically tailored to the subjects you're pouring effort into. Research on cognitive performance confirms this. Studies consistently show that rigorous academic training, like that undertaken by university students, leads to improvements in working memory, your mental workspace for manipulating information, cognitive flexibility, the ability to switch between different concepts or tasks, and overall problem-solving abilities. CS students, for instance, demonstrably improve their logical reasoning and analytical skills through the constant practice of designing, implementing, and debugging complex systems. Now, here's where many people fall into a trap: cognitive bias. We often hear people say, "I'm just not wired for math," or "I don't have the brain for coding," or "psychology theory just goes over my head." Often, this isn't a reflection of their actual capacity, but rather a belief system reinforced by confirmation bias. They might struggle initially, which is normal and actually necessary for neuroplastic change. Interpret that struggle as proof of inability, and then subconsciously avoid putting in the sustained effort required for the brain to adapt. They focus on the failures and ignore the small progresses. The hard evidence, however, points in the opposite direction. Studies on expertise and skill acquisition, like the work on deliberate practice, emphasize that consistent, focused, challenging effort is the key differentiator between average and high performance, often outweighing perceived natural talent. The very act of struggling, persisting through difficulty, is the signal your brain needs to initiate those powerful neuroplastic changes. The students who see the most cognitive gains aren't necessarily ones who find it easy, they're often the ones who push through the difficulty. Psychology students offer another fascinating angle. Their intense study of human behavior, cognition, emotion, and mental processes doesn't just fill their heads with facts, it can subtly reshape their own cognitive and emotional functioning. Studies suggest that learning about psychological principles can enhance empathy, improve theory of mind, the ability to understand others' perspectives, and even foster better emotional regulation strategies as they gain insight into psychological mechanisms. They also develop sophisticated critical thinking skills by constantly evaluating theories, research methodologies, and evidence related to complex, often ambiguous, human phenomena. However, it's crucial to acknowledge the biological reality: pushing hard isn't without potential cost if not managed. Intense, prolonged study, especially under pressure like exam periods, triggers the release of cortisol, the stress hormone. While short bursts of stress can be motivating, chronic stress can actually be detrimental to learning and memory. High, sustained cortisol levels can impair neuroplasticity and, in extreme cases, even lead to shrinkage in areas like the hippocampus. This is hard evidence too. And then there's sleep. Intense study requires intense recovery. Sleep is absolutely critical for memory consolidation, the process where your brain sorts, strengthens, and integrates the information you learned while awake. Pulling all-nighters consistently might feel like hard work, but the evidence clearly shows it undermines the very cognitive processes you're trying to enhance, impairing attention, memory recall, and problem-solving ability. So, what's the big takeaway? Studying hard, truly pushing your cognitive boundaries in demanding fields like computer science or psychology, is a potent catalyst for real, measurable brain change. It enhances gray matter, strengthens synaptic connections, boosts cognitive functions like memory and problem solving, and refines critical thinking. This isn't just about passing exams, it's about fundamentally upgrading your cognitive hardware through effort. But beware of the bias that tells you struggle equals inability. The struggle is the mechanism of growth. Embrace the difficulty, understand that it's the signal for your brain to adapt. However, balance that intensity with adequate rest, sleep, and stress management, because burnout is real and counterproductive. The science is clear: your brain is built to change in response to demand. The hard work isn't just something you do, it's something that actively builds a more capable version of you.